So we're going to move on to acceleration due to gravity. Um, I want to lead off with a little video here. I want to show this. Okay, so this is actually footage of one of the Apollo missions. I can't remember what it was. And it comes, the reason why they're up there is because a guy named Galileo discovered that, well, I'll play it and I'll talk about it after. So let's play this.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here and hopefully they'll hit the ground at the same time. How about that? Which proves that Mr. Galileo was correct in his findings.
All right, so the reason that they did that, they brought that hammer and feather up to the moon with them, was because before Galileo, everybody, well, just probably rightly assumed that something like a rock and something like a feather would fall to the ground at different times, and that was just common sense, right? Rocks fall faster than feathers, so they said, well, more heavy things fall to the ground faster than lighter things. But what Galileo discovered is that it actually doesn't matter. Things of all different masses all accelerate down to the ground at the same rate, at negative 9.81 meters per second squared. And the reason why the moon was so important is because the moon doesn't have an atmosphere, or it has virtually no atmosphere. It's so thin. So if you drop a feather and a rock and a hammer, then air resistance doesn't play a big part. So if it wasn't for the air resistance that a feather, it catches the air and kind of floats down to the ground. If it wasn't for that, it would fall at the same rate as a rock or a hammer. So that's just what I've outlined in that first paragraph there. This quick lab, that'll be optional for you guys if you want to do that. So what Galileo did, though, and he probably doesn't get near enough credit, he's really probably the first scientist there ever was. He took this question and he said, well, let's test it. So he went up on top of the Leaning Tower of Pisa and dropped different objects of different masses and just put it to the test to see when they actually would hit the ground. He didn't take things like feathers into account because I think he had the idea that it was probably air resistance that was the cause of that. The problem, however, though, if you start dropping things off of a tower just to see, when they're going to hit the ground, is how can you be totally sure that you're going to drop them at the exact same time? So this is where error comes in, right? So like a good scientist, what Galileo ended up doing was he ended up rolling objects down a ramp. He had like a ramp system set up with different mass objects. They were actually different balls, but they were all the exact same size, same smoothness. He kept all the variables the same, but he changed the mass of them. So really, the only thing that it could be, like in this situation of rolling these things down a ramp, was the mass, right? They were exactly the same in every way other than their mass. But doing this, he was able to find that they rolled down that ramp at the exact same time every time. And he put a little board here. So when he took the board away, they would all fall at the exact same time. So a really good scientific experiment before science was even really a thing. All right, so returning to the acceleration of freely falling objects. So this is the Earth, let's say. We've got gravity pulling down in all direct, like inward, everywhere you go on the Earth, right? And that's what's really responsible for this acceleration due to gravity. We call that acceleration due to gravity instead of A, we're going to call that G, because it's the same everywhere on the surface of the Earth. Not exactly the same, because really you might get like a mountain or something on the Earth here, and it would be a little bit less at the top of that mountain than it would be on Earth, just a little bit. And actually, if you go up into the International Space Station, so say you're floating around out here. This isn't the scale, by the way. The acceleration due to gravity up here for astronauts is actually still something. It's 8.7. It's actually not that much lower than it is here on Earth, which is kind of strange, right? Because don't they float around in space? We're going to talk about that more in circular motion unit, but yeah, that's for now. We're just going to, you have to trust me on that one. So just know for now, though, remember like in the last video I was saying that acceleration and force have a lot to do with each other. When you think about what direction and acceleration is, you think about like that bungee cord analogy that I was using. The same type of thing with Earth, right? The force or like that is happening on Earth is always pushing straight down. So the acceleration is also always straight down. Even when you throw something up in the air, if I throw an object up into the air, the acceleration was downward the entire time as soon as it left my hand. It's accelerating upward while I'm throwing it in the middle of me pushing my hand upward. But once it leaves my hand, the acceleration is downward the entire time because the force is downward the entire time. That's a really important concept to know. So I've got these examples. They're really similar to the ones that you guys have already done so far. So I'm going to let you guys go ahead and do them on your own. The only thing I would point your attention to, and something that kind of gets everybody, is this first question. It says, on planet physics is hell, an object dropped from rest. The word rest, that really is a number. From rest is saying 0 meters per second. So that's V1. That's our velocity. So just make sure you notice that in the questions that you're going to do. So V1 from rest. And then fill it in, and really it's everything that we've done before, but we've got a negative acceleration in the end, and we get, so that means it's going down. And actually I lied. I am going to show you number 7. So for these questions where it's going to say how high did something go. So if I throw, let's say like this brush up in the air. So I throw it up and it comes back down. The question is, how high did it go? There's one bit of key information here that isn't going to be obvious or in the question. It's not going to say that it's going a certain speed at the end. But what we can infer is that if I throw this thing up in the air, how fast is it going right at the top? I know, like maybe I'm like moving it sideways or something, but let's pretend I like, I could throw it like perfectly straight up in the air. So I move it up in the air. It's gonna go up. It's gonna come to a stop before it comes back down again. It has to. It has to stop before it can start going the other direction. So one key bit of information here is that VF or V2, the final velocity, is gonna be 0. So that's the key bit there. So that brings me back to example 7 here. We know all the stuff, right? We know that the acceleration is negative 9.81 because that's what it is on Earth. That's on your formula sheet too, by the way, and you should just memorize it. The question tells us that it's being thrown up in the air, so positive 15 meters per second, and V2 is equal to 0. That's the key bit there. And just remember that if I throw this thing up in the air, comes to a stop and then back down again, that if you figure out the time, that's only the time to get to the top. If I need to figure out how long it was actually in the air for, you're going to have to double that. So it's going to be 1.53 seconds to get to the top. It's going to be 2 times that to go all the way. So that'd be 3.06 seconds. So quickly, I'd like you guys to read pages 58 and 59 from the textbook. And then we're going to move on to practice problems.